Hola, hi, this is Al, your statistics instructor. Let's get to work. So, in this video, my intention is to do with you a homework problem. I would like to work with you this particular problem that we left as an exercise at the end of Friday's lecture. Okay, we ran out of time. So anyway, let's try and do this problem together. So what we would like to do is, as you can see here, the process that we have is a moving average, okay, of first order. And what we would like to do is computing the spectral density and the normalized spectral density for that MA1 process. Okay, here we go. So, first, let me write down the process that we're dealing with. So, process, it's an MA. Okay, so what we have is Y. What we have is Y sub T. It's equal to WT, an innovation, plus beta times WT, well, WT minus 1, okay? Where, as usual, WT has a normal distribution. So it's normally distributed, means zero variance, sigma squared so we have sigma squared for that Gaussian white noise. Okay? So, solution. First, let me remind you what's the definition of the spectral density. Okay? So what we have here is F at W equals, then we have the summation going from k equals negative infinity to infinity of the autocovariance function gamma evaluated at lag k, okay, gamma at k times e to the power minus 2 times pi w I k, where I is the square root of negative 1, okay? So let me just remind you about that, where I equals square root of negative 1. Okay, so we would like to apply that definition. That would be the spectral density. Okay. So first we're going to find the spectral density, and then we're going to find the normalized spectral density. Okay, so spectral density. So as you can see, if we want to apply the definition, first we have to find the autocovariance function. gamma at k. Okay, so let's say that. So let's find gamma at k, the autocovariance function. Okay, here we go. So let's proceed as if we were taking a test. Okay, so let's find gamma at 0 first. So gamma at 0, that would be well, before we do that, okay, just for completeness, let's find the expected value of our process. Okay, let's find the expected value of our process. So what we have would be the expected value of W at t plus beta times W at t minus 1. So we know that the expected value is linear, or in other words, the expected value of a sum is the sum of expected values. So what we would have is the expected value of W at t. Beta is a constant, so we can pull it out, right? We can factor that out. And then we have expected value of W at t plus beta expected value of W at t minus 1. By assumption, the expected value for Wt for every time t is 0. So we end up with 0 plus 0, that's just 0, right? Okay, perfect. So our process has a mean or expected value of 0. Now, let's find gamma, the autocovariance function at lag 0. Okay, so let's find that. Remember that that would be just the covariance of yt and yt. Oops. There we are. Okay, so now we have shown that the expected value of our process is 0. So the covariance in this case is going to be just the expected value of yt squared. Okay, so let me write that one down here. Oops. Another way of thinking about this is as follows. So since the expected value of our process is 0, right, the expected value of yt squared happens to be the variance of yt. Okay? There we are. Okay, so let's find it. Let me find it here underneath. So in this case, will be the variance of, this is the definition of yt, right, or y at t. So we have W at t plus beta times W at t minus 1. Okay, let me continue here on the next line. So we have the variance of a sum. Since we have independence, let me write that down using the independence of those W's. By assumption, the WT's are normally distributed mean 0 variance sigma squared, and they are I, D. Okay. So we have the variance of a sum of independent terms. It's the same as the sum of variances. Let me copy paste this. So since we're pulling out that constant, remember that we have to square it. So let's square it, variance here. And then by assumption, the variance of the w's is sigma squared. Let me copy paste that. So we have sigma squared plus beta squared times, again, variance for w at time t minus 1, sigma squared. Okay? So we have a gamma at 0. Okay? We're done with that one. Now let us find gamma at 1. Okay? So let's find gamma at 1. Let's find the autocovariance function at lag 1. So now it would be the covariance between yt and yt minus 1. Okay? Now, I'm going to need more room here, so let me continue on the next line. So it's going to be the covariance between wt plus beta wt minus 1. That's just the definition of the process. Now let me do the same with t minus 1. So let me copy paste this guy, and then I'm going to modify that accordingly. So we would have t minus 1 here, and we would have t minus 2 here. Agreed? Okay. So, bear in mind again that by assumption the w's are IID, independent and identically distributed. So let me use the independence. And then we're going to have the following. It is going to be just like this. We have the covariance of two linear functions. Let me do the math, and using the independence, we're going to be able to eventually get rid of some of those terms. Okay, so let me write down what we have here. It would be the covariance between wt and wt minus 1. That will be the first term. Agreed? Now we would have covariance between wt and beta wt minus 2. Okay? So let me do that one here. Agreed? So we have wt, wt minus 1, wt, and beta wt minus 2. Okay? 2 more to go. So now what we need is beta times covariance of wt minus 1 and wt minus 1. So let me do that one here. So we have this one, and we have wt minus 1. And then finally, we have wt, well, beta wt minus 1 and beta wt minus 2. Okay, so let's do that one. Let me place it below so you can see it. So beta wt minus 1, beta wt minus 2. Agreed? Okay. Now, by independence, let me use that fact. what we're going to have is that this first term, the covariance between WT and WT minus 1, is going to be, since they are independent, the covariance between them is just 0. Same goes for this one. I mean, you could pull out that beta coefficient, right? And then you would have the covariance between WT and WT minus 2, which is also 0 by independence. Now, this one here, we could pull out that beta coefficient. We could factor it out. And then you would have the covariance between WT minus 1 and WT minus 1, which happens to be the same as beta times the variance of WT minus 1. Let me copy paste this. Let me just say variance. Okay, finally, you could pull out these two betas, and then it would be beta times beta, so that's beta squared. But again, using the fact that WT minus 1 and WT minus 2 are independent, you end up with a 0. Okay? So finally, the only term that survives is beta variance of the W's, which is just sigma squared. Okay? So let me just conclude that the autocovariance function at lag 1 happens to be beta times sigma squared of W. Let me borrow this one from here. Okay, next, let's find the autocovariance function at lag 2. Okay, so let me copy this one. And then I'm going to modify that accordingly. So now we want gamma, the autocovariance function at lag 2. So instead of a 1, we will have a 2 there instead. So just like before, let me use the definition of your process. So it would be WT plus beta WT minus 1, and then I would need to change the sub-indices accordingly for this one. So again, let me copy-paste that from here, okay? And yes, let's do it on the next line. So this one doesn't change. That's just the definition of the process at time t. This one will change. This is the definition of the process at time t minus 2. You guys agree? Okay. So now let's do what we did before. It's the covariance between two linear functions of the innovations, the W's. So let's just do the math and then just use the properties that we know, the expected value and the variance and the independence of the WT terms, okay? So first term, here what we have is covariance between WT and WT minus 2, perfect. Then we have plus, and then we have WT beta WT minus 3. So let's do that one. Let me pull out that constant, that beta. Now, next term, okay? We need beta WT minus 1 and WT minus 2. So let's do that term there. So we have beta WT minus 1 and then WT minus 2. And finally, the fourth term would be beta wt minus 1 and beta wt minus 3, the covariance between those two terms. So let me copy paste this, modify accordingly, and then factor out that beta times beta, which is beta squared. So here we are. Again, just like last time, for the autocovariance function at lab 1, we will use the independence between the w's to simplify that expression. So the first term, wt, is independent of wt minus 1, therefore the covariance between them is 0. Then here, same idea, 0, using the independence between wt and wt minus 3. The covariance between wt minus 1 and wt minus 2, we get to factor out that beta. Let me pull it here. What you have is again a 0. Fourth and last term. Again, covariance between wt minus 1 and wt minus 3 is 0. So we have 0 here, we have 0 here, we have 0 here. Okay? So 0. In the end, gamma at 2 equals 0. We could use a similar argument for any k that is greater than 2. So let me just say that. Similarly, for k greater than 2, we could show that gamma at k for that sort of lag is going to be 0. Okay? Okay. So let us just summarize what we have. Okay? So what we have here is that gamma at lag 0 is, let me show you this. Gamma at 0 is sigma squared of w plus beta squared sigma squared of w. Okay? So let me actually factor out one of these guys so we can have something nicer. So let me rewrite it like this, times 1 plus beta squared. Okay, so gamma at 0, the autocovariance function at lag 0, sigma squared times 1 plus beta squared. Okay, that's one. The other one that we have is gamma at 1. Gamma at 1 happens to be beta times sigma squared of w. Okay? Finally, we showed that gamma at 2, the autocovariance function, is 0 for any lag that is 2 or greater than 2. Okay? So now that we have that, we could apply the definition for spectral density. Okay? So let me write that down. That now we're going to find the spectral density. So let me just copy paste the definition, and then we're going to apply it. there. So f at w, it's the summation, k goes from negative infinity to infinity of gamma at k, right? The autocovariance function at lag k times e to the negative 2 times pi wi times k. Okay? Well, now let's break that down into three terms. The first one, it's going to be gamma at 0. Note that e to the 0 power is just 1. So that's one of the terms. Now, let me do that same sum, but I'm going to do that sum. K goes from negative infinity to negative 1. Okay? Plus, I'm going to do this sum, and I'm going to remove when k equals 0 and when k goes from negative infinity to negative 1. I'm going to start from 1 to infinity. So I just re-expressed the entire series that we have here and rewrote that in terms of three terms. Okay? Now, remember that gamma at k equals the same, is the same as gamma at negative k. Okay? So now I'm going to be doing this from 1 to infinity, and we have negative k here. Now note, for instance, here, for the original one, you have that negative sign here. Let me place it with k. It's the same thing that we had. But now, for instance, when k equals negative 1, then negative k equals positive 1. When k equals negative 2, well, minus k is positive 2, and so on. So what I could do is just have that instead. Okay? And now, finally, again, just let me use the fact that gamma at negative k and gamma at k are the same. So let me rewrite this. Let me just say that. We call that gamma at negative k. Just this part here. Well, gamma, that's the one I want, right? The autocovariance function at negative k is the same as the autocovariance function at k. So that's why we can do this. Now, let me rewrite this as follows. Gamma at k, the autocovariance function, it's a common factor. So what we end up having here is something that looks like this. Gamma at k times e to the power 2 pi wik plus e to the power negative 2 pi wik. Okay? Oh no, that's too much. Let me then just copy paste this one and change the sign. There we are. Agreed? So now let me just remind you about this Euler's formula. Euler's formula. Remember that e to the power I x for any x, right, equals cosine of x plus I sine of x. Okay? Okay, so now let us apply this for this particular angle, if we want to call it that. Okay, so here we go. This, using Euler's formula, would be cosine of two pi w k, no I needed here, plus I times sine of that angle. Okay, make sense? Now let's do the same, but now instead of having 2 pi w I k, we are going to have the negative version of that same exponent. So you would have cosine of minus 2 pi w k plus, and then I sine of 2 pi w k, with a negative sign. Okay, now let me just remind you that cosine of, let me say, negative alpha to refer to a generic angle equals cosine of alpha, right? And you also have the sine of negative alpha equals negative sine of alpha. Okay? So, what we have here is that the cosine of negative 2 pi w k equals the same as cosine of 2 pi w k. And sine of negative 2 pi w k is the same as minus sine of that same angle, and then this one is multiplied by I. Okay? So now let me call this one here 1. Let me call this one 2. So note that what we want here is e to the power 2 pi w I k plus e to the negative 2 times pi w I k. So we need the sum of these two exponentials. So 1 plus 2 is going to be equal to the following expression. This plus this equals cosine of 2 pi w k plus cosine of 2 pi w k. So that's 2 times that cosine, right? And then you have I sine of 2 pi w k minus I sine sine of 2 pi w k. So these two terms cancel out, okay? So from 1 and 2 we have, and this is what we have, that the sum of these two exponentials equals 2 times cosine of 2 pi w k. Okay. So let me just go back to what we have up here. Sorry. Going back to what we have here is gamma at 0 plus instead of having gamma at k, well, the summation k goes from 1 to infinity of gamma at k times e to the power 2 pi w I k plus e to the power negative 2 times pi w I k, we could rewrite that just like this. We're going to have 2 and then cosine of 2 pi w k. Okay, let me change that one here. Just here. Let me get rid of this one here. Okay, agreed? Okay, so finally, so what we have is gamma at 0. So, well, first let me say that we have f at w, the spectral density, is going to be gamma at 0. In our particular case, let me remind you that what you showed is that gamma at 0 is given by this expression that we have here. Okay, variance of the w's times 1 plus beta squared. So that's what we're going to have here. Plus, and what we're going to have is just 2 times gamma at 1, because remember that when k equals 2, you will have 0. And if k is greater than 2, you still have a 0. Okay? So the only one that matters is gamma at 1. So let me copy paste that one and apply the definition. So we have gamma at 0 plus 2 times gamma at 1, which is going to be just this, times cosine of 2 pi w times 1, that's just cosine of 2 pi w. Okay? And then when k equals 2, gamma at 2 is 0, 0 times whatever, then we're going to kill it. This cosine is not going to matter. Gamma at 3, you know, again, it's going to kill that cosine here, and so on. So that's what you end up with here. Okay? That will be the spectral density for your moving average of first order. Okay? Now, let's try and find the normalized spectral density.